Okay. So where are we? We are in what we call electromagnetism. And we've had a 2-hour lecture last time where we initiated this entire area of electromagnetism. And we said the electro is the electricity and magnetism. They're both because of the same intrinsic property, Q. I'll be using the small alphabet Q. You can use the capital one if you want. It's basically this intrinsic property, charge, which gives rise to electricity, which gives rise to magnetism, which gives rise to an electromagnetic disturbance, which is nothing but an electromagnetic wave, which is our light wave. So light has an electromagnetic nature. Great. This summary, which I've just given you in this few lines, was put forward by Maxwell. I think it's James Clerk Maxwell. Sometime in the 19th century, mid-19th century, 1845 maybe, or 50. Before that, there was a lot of work going on in electricity, in magnetism, but they were being dealt with in different countries with different scientists, with different measuring units, and nobody knew that there was a connectivity between electricity and magnetism, between the electric field and magnetic field. Nobody. It was around 1840s, 50s. Maxwell, who's considered the father of electromagnetism, through his great theoretical works and observations of the works done by others, he came to these conclusions. And of course, his summaries and his conclusions and his little theoretical proofs were used by other people around who are experimenters. And they were able to see the results that Maxwell was talking about. And it was only towards the end of the 19th century, 1870, I think, or 75, that experiments were done by Hendrik Hertz, a German, Hertz, which showed to the world that light waves were nothing but electromagnetic waves. A light wave or light is a disturbance of the electric field and magnetic field. But light was being dealt with from the time of Newton. Newton spoke about light. 17th century. And we are in 19th century. 17th century. He said light probably is a stream of particles according to Newton. He said that because he could explain simple phenomena like reflection, refraction, dispersion, etc. Shadow formations. Because he was able to use geometry and he was able to show these phenomena and prove the laws of reflection or refraction in some way. People did not give too much of stress to the fact that light could have some other nature. And as different phenomena started getting noticed, as experiments became more and more sophisticated, certain more subtle phenomena started getting noticed about light. Then this simple explanation of light being a stream of particles was not sufficient. Hence, people did not know the nature of light, but they carried out all kinds of experiments with light. Right through the 17th century, 18th century, towards the end of the 19th century, through the works done by Maxwell and experiments done by Hendrik Hertz, that people got to know the nature of light. That it is nothing but a disturbance of the electric field and the magnetic field. The electric field changing with time, generating a magnetic field, the magnetic field changing with time, generating an electric field, and hence generating a wave, a form of energy. If it falls within a certain range, which the human eye can perceive, the visible range, we then spoke about light. But in general, there is a huge spectrum of electromagnetic waves from that narrow band of visible range which the human being can use. And then you have on one side waves with longer wavelengths like radio waves, microwaves. And as you move into that bigger and bigger and bigger long waves, and on the other side, you have the other range from ultraviolet to X-rays to gamma rays, smaller and smaller wavelengths. This whole spectrum, which finally was called the Maxwell spectrum, is very wide and vast. We, as living creatures, the human beings, can see the world through a very narrow range. There are a number of creatures discovered, not yet discovered, which can see beyond this range, in the infrared range or the ultraviolet range. They can, which we cannot. So our world, our perspective of the world is very narrow. Let's not digress into that. The idea was that when you see the works of Maxwell, and as you move and move and move and move to the beginning, you find that everything that we have discussed till now, the electricity, the magnetism, the electromagnetic induction, the electromagnetic waves, is all because of this intrinsic property, charge. We have spent the entire first year with the intrinsic property mass. Newton's word. Our first year was mostly just mechanics, where we took a particle or a rigid body and we spoke about it having a property mass. It is also an intrinsic property. If you take a rigid body, break it up into particles, break up the particles into molecules, and break up the molecules into atoms, and break up the atoms into atomic particles, and pick up whatever smallest particle that you finally come to, it will have mass. The property we say is intrinsic. You can't get rid of it. Similarly, along with mass, there's another property, charge. You cannot get rid of charge. It is intrinsic. So when I took the rigid body or I took a particle in mechanics, I only spoke about mass. Charge was there. I kept it silent. I looked at the entire rigid body dynamics only with the property mass, because I was clear that I'm going to talk about the intrinsic property charge separately. And then as I move into electromagnetism, because I already have a vocabulary of mass, next time when I take a particle, I will say a particle, it has charge Q, mass M. See? Why? Because in that problem, I needed mass. Why? Because there was a gravitational force involved. In that problem, I needed charge. Why? Because there was a Coulomb's force involved, an electric force involved. There was a gravitational force involved in that dynamic situation. This, once we are matured in this area, then we will start talking of particles having both the properties. In my last class, I told you certain things. I said that when I say that I'm taking a particle which has charge Q1, forget particle. Let us say I put my hand in the pocket and I remove a coin. This coin has got millions of charges. Millions. You know very well. The basic building block of any material, including this coin, is an atom. It could be a multi-electron layered atom. And it could be having millions of atoms, millions of electrons and protons, millions and millions and millions. But sir, this coin has millions and millions of charges, but they are balanced. When I say I've taken a coin with charge Q1, I only mean the unbalanced value, not the millions and millions which are balanced. The unbalanced value, the excess charge. Let us accept the fact that we know the structure of the atom to a certain extent in a rough way. It's a pretty neutral material which has a central concentrated positive area, and outside there are some negative clouds. If I were to remove some of the negative cloud, erase it off or rub it off, that atom becomes positively charged because the excess is positive. Only the difference is what I write. It is only that difference that we say particle charge Q, only that unbalanced excess charge. And it is only that unbalanced excess charge which creates the whole of electromagnetism. It is not the balanced charges. I'm standing here, around me, there are millions and millions of charges in the air around. They are balanced. Maybe there are a few pockets here and there where there is some imbalance. Look at the skin on my hand. It is made up of atoms. Atom, 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 molecule, 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 skin. If I look under the microscope, there is a hazy cloud of negatives, which is the electrons, isn't it? I can just do this, rub it against my shirt, and this part of my skin will get charged. If I've rubbed off the electrons, or if it has taken electrons from my shirt, then it will have excess negative. If the electrons have got wiped off from here, it will become excess positive. I have charged it. So easy to charge. But as I wave my hand around, after a few minutes, when I come back and I check, there is no charge. Some negatives from the air got attracted towards the positive patch and they've neutralized it. Understand this aspect of things. Okay. So as I was discussing in my last class, that this is the excess charge, then I made another statement. The charge is quantized. That means it's not a continuous kind of a property, charge. As I go down to the smaller and smaller and smaller and smaller, smaller and smaller, and I come to the smallest value of charge, the quantum value of charge, the smallest value of charge, it has a value 1.6 into 10 raised to minus 90 with some measuring units for charge, which I'll just talk about. Coulombs. After the scientist Coulomb, who did a lot of work in this area of electromagnetism, and so we give him respects by saying that in the international units of measurements, let's give the measuring unit for charge as coulombs. All right, okay. So I went to the smallest and the smallest and the smallest value I came to. It was this. What do you mean smallest? After this, it went to zero. Straight jump to zero. This is the quantum value of charge, the smallest value of charge. Which means that when I say that the particle is of charge Q, it means it's in multiples of E. E was the alphabet which was reserved for the quantum value of charge. So every charge that I come across in life will be in multiples of E. The quantum value of the Indian rupee today, I don't think is 10 paisa, 5 paisa, 25 paisa. No, it's, I think, 50 paisa. No, maybe 1 rupee. Today, the smallest value of the rupee is, money is 1 rupee. If I go to the pawn shop, he either gives me back something which is in multiples of 1 rupee, or he says 0. Because he's not able to return me 50 paisa, he might pull out 1 sweet and give it to me. Charge is quantized. There's a quantum value, a smallest value given to it, a discrete value. 1.6 into 10 raised to minus 19 coulombs. Who found out this value and who discovered it? That will come later on while we are discussing electromagnetism. When a small experiment will be mentioned and you'll be told about it. Right now, you're collecting certain data which you require to start the chapter. Charge is quantized and the smallest value is this, and the measuring unit for charge is going to be coulombs, let us accept. We discussed in the last class. Then we spoke about Benjamin Franklin. Much before Benjamin Franklin, through his little simple experiments, started making the world aware of this intrinsic property charge. Rubbing 2 pieces, maybe a cloth and a glass rod, and then talking about how the silk cloth is attracted towards the glass, or the glass is attracted towards, or it is repelled by another glass piece which is rubbed by the same cloth, etc. And through his small experiments, Benjamin Franklin told the world, number one, that there are 2 kinds of charges. Yes? And so the committee of scientists, which was looking at the little experiments done by Benjamin Franklin, gave him the authority to name these 2 charges. He called one positive and the other one negative. But look at the way it has gone into our vocabulary, that we actually think there is something called negative charge and positive charge. These are just 2 names given by Benjamin Franklin, that there are 2 kinds of charges, sir. Unlike mass, which is only of one kind, charge, the intrinsic property, has 2 kinds. What do you call them? Benjamin Franklin says positive and negative. And look at the way we start thinking in our head. And we argue. No, this is negative. No, this is positive. It's just one kind and one kind. One kind and the other kind. That's all. There could have been named anything. Okay. So charge is quantized, quantum value, charges are of 2 kinds, positive, negative. And Benjamin Franklin said that like charges, that means 2 positives, when you bring them close enough, they will repel. 2 negatives, when you bring them close enough, they'll repel. Like charges repel. And unlike charges, 1 positive, negative will attract. He even probably went to the extent of saying that this force, which is attraction or repulsion, is of the same nature. If 2 positives of the same value repel with a certain force at a certain distance, then a positive with a particular value and the negative with the same value will attract at the same distance, when brought at that distance r, will attract with the same force. Repel. The force, the study of this force between two charges, the quantification of this force, that means the formula to get this force, the quantitative study was done by Coulomb. Much later on. Coulomb quantified this force, this repulsion, attraction, the force between any two charges, Q1 and Q2, when they are brought close enough at some distance r, then they will experience, Coulomb said, a tug. Maybe a push, maybe a pull. And he quantified it. We don't get very deep into that experiment. As I told you, I will be taking numericals later on, and then I will tell you that this numerical is based on the experiment done by Coulomb, and this equipment is called the torsional balance. So Coulomb used the torsional balance to quantify the force. What force? Electric force between two charges, two particles which have charges Q1 and Q2. And he quantified it, which we have discussed in the last class. And he said that this, see, I'm writing this to tell you that it's the electric force I'm talking about, because here when I took two particles, not guys with dimensions, guys whose dimensions are not very important, but with the intrinsic property M1, another one M2, separated by a distance this, then I said, Newton said, gravitational force. Here I say, electric force. Coulomb's force, Newton's force, Coulomb's force, gravitational force, electric force. Very similar in structure. And he quantified it. He says, take any two particles which have charges Q1 and Q2 separated by a distance r, then the electric force in magnitude is proportional to the product of the two charges, inversely proportional to the distance between the two squared. And hence in magnitude, the electric force of the Coulomb's force is equal to. When this proportionality was removed, a K was put by Coulomb. The magnitude of the gravitational force between the two is proportional to the product M1 and M2. Is inversely proportional to the square of the distance between the two. Then, when I remove this proportionality, the gravitational force in magnitude is equal to, I put G. Looks very, very similar. Intrinsic property mass, intrinsic property charge, everything looks okay. This This quantification and experiment was not done by Newton, it was done by Cavendish. And this G was a mathematical proportionality constant. That means to balance the left and the right, I got a factor G. We called it the universal constant, whatever. It took some value. So when I took M1 and M2 in some medium, then I took M1 and M2 in another medium, the gravitational force remained the same and the value of G remained the same. But this was not the case here. This was not just a mathematical balancing constant, proportionality constant. When Q1 and Q2 were in a vacuum, I got a certain value of force. That means Q1, Q1, Q2 are in a vacuum. Then I took Q1, Q2 are same in air. When I took it in a vacuum, I got something. When I took it in air, I got another value. This has not changed, this has not changed, this has not changed. Who's changed? Then I took it in oil. Again, I got the third value. As I kept changing the medium, this is the same, this is the same, this is the same. This kept changing. That is where we end the comparison. This is a mathematical proportionality constant, a gravitational constant, and this guy, K, is not a constant. It is a chap who varies with the medium. There's a medium factor involved. There will be a balancing factor, but there is a medium factor involved. Coulomb, in the beginning, did not know it. Subsequently, he must have noticed it. But he was still not aware of the value of K. How to format K. As electromagnetism moved and moved and moved and moved and moved and moved and moved, you'll be surprised. It was only somewhere in the mid-19th century that people really got a feel of K. In some of your books and some of your sirs keep writing this K. I do not want my students to do that. It is totally wrong. It's not done anywhere in the world. We are going to start using the value of K, which will be presented to us much later, but we start using it straight away. All modern books of electromagnetism start using it. Now, I call this the electric force. But because I took these two particles and kept them static to start with, of course, after that they experience a pull and they start moving, but to start with, and hence I call this electrostatic force. Electric force, you can say no problems, or electrostatic force because the charges are under static conditions. And everything that I study where the charges are going to be static, I call that chapter electrostatics, which is part of electromagnetism, which is the first introductory chapter, which gives us an insight into the property charge. If the whole of electromagnetism is because of property charge, then I have to get to know my charge better and better and better and better as I move into this chapter. I have to enrich my ideas of this property charge, what it does. That's exactly what Maxwell showed. He said, you take charge under static conditions, around the charge you will see an electric field. You will experience an electric field. You will experience a disturbance, an electric field. When you move charge, you will experience an electric field, but along with that, you will experience a magnetic field when the charge is moved. When the charge is accelerated, you will experience an electric field, you will experience a magnetic field, and you will experience an electromagnetic disturbance when the charge accelerates. An electromagnetic wave also will get generated in that zone, along with an electric. See, it is charge. Charge under different dynamic conditions is giving you the phenomena of electricity. Moving charge, electricity. Static, moving, electricity. Current, we call it. Electric current. Electric current gives you outside the conducting material which is carrying moving charge, which is carrying current. Outside this wire, you will experience an electric field, you will experience a magnetic field. And if this charge is accelerating, you will experience an electromagnetic wave. And if it falls within your visible range, you will see light. You don't see light, you experience and perceive light. Wow, it's all charge. This was the greatest contribution of Maxwell. Nobody could connect it so well as he did it. And hence, towards the end of the 19th century, 1875, 80, Einstein started making his presence felt. And Einstein, towards the end of the 19th century, beginning of the 20th century, Einstein said that the father of electromagnetism is Maxwell and the father of mechanics is Newton. I'm standing on the shoulders of Newton and Maxwell, and I am now moving ahead with ideas which have come because of the work done by Newton and Maxwell. Einstein got deeper into the electromagnetic phenomena. He got deeper into the electromagnetic waves. He went into the micro level and he started giving explanations to phenomena which were noticed because the equipments were getting more and more sophisticated and certain behavior of light was getting noticed. And it was Einstein who started giving explanations by using quantum physics. Quantum physics. You go down to that level where everything is in discrete values. The continuity of water, when you go deep down into water, you find H2O molecules. See, discrete particles. At that quantized level, Newton started looking at certain phenomena which were manifesting themselves, becoming visible to the common man. He gave explanations which went very deep into the quantum world. Quantum physics is a fantastic area in future for those who want to get into the depths of science. You can design smart material. You can get into the levels at which, if you tinker at the quantum level, any material, you can change its entire nature, its behavior. Okay, that's the future. So we are clear. Let's come back. So it was Coulomb who quantified that force between charges. And this, to give respects to Coulomb, through an experiment, the whole apparatus was called the torsion balance. This formulation also came from the same equipment, the torsion balance, which was done by Cavendish. But Coulomb carried out this experiment much before Cavendish carried out this experiment. Though we studied this before, that's okay, because that is how our syllabus is. But this was done much before. Probably Cavendish took ideas from this experiment, maybe. But it's not the other way around. Coulomb did it first. We'll talk about the simple experiment. So because Coulomb quantified this force between two charges, he was given respect, and this is called the Coulomb's law in electrostatics, where charges are under static conditions. Coulomb did not have an idea of this. Today, when you study electromagnetism, that committee of scientists has put down the subject for you in a certain chronological order, and they want you to study the subject with the correct value of K. Had we followed Coulomb's nomenclature, had we continued with this K, saying that K in a vacuum has this much value, K in air has this much value, K in oil has this much value, had we done that, and had we moved from electrostatics into charges moving into current electricity, and then into magnetism, and then into electromagnetic induction, and then into electromagnetic waves, let us say, then this K, as I told you last time, if I started off with a simple crisp letter K, then towards the end of electromagnetism, which is the end of the 19th century, would have taken a shape which would have been unmanageable. So, had I started with K in electrostatics and moved to current electricity, then this would have become like this. Then I would have moved into magnetism. It would have become like this. And had I moved into electromagnetic induction, it would have become like this. And then further, had I moved into electromagnetic disturbance, it would have become like this. It would have become something very ugly, unmanageable, a devil. The end of electromagnetism would have been so dense and so difficult to understand. You have made a simple phenomena into a devil. And so, that committee of scientists which put down the chapter of electromagnetism in a certain chronological order decided to divide the ugliness, little bit of the ugliness, the horns in electrostatics, the ears in magnetism, the eyes and this in electromagnetic induction, and the teeth, the sharp teeth in the chapter of electromagnetic waves. They split it up. They made the ugliness more palatable. So that when you come to the end, where you are looking at simple light waves, it is something which is simple and manageable, because you have already taken care of the ugliness in the beginning. And so we accept that. We accept the way in which electromagnetism has been presented to us by that brilliant, intelligent committee which controls the subject, which presents the subject to the student of science. We accept. And we say that when we write the Coulomb's law, we are going to say in magnitude, the Coulomb's law is equal to 1 upon 4 pi epsilon naught 4 pi. Number 4 pi of geometry, 4 pi epsilon naught Q1, Q2 upon R square. Coulomb would have never ever been able to think of K being something like this. You as a student, even now, even after I've explained you how it was done, you would still find it difficult to accept that how did this guy find out that the proportionality once removed comes to this kind of a terrible looking expression. It doesn't. I told you how it has been brought forward, the ugliness has been distributed, and in electrostatics, this much ugliness comes in this. By itself, this expression reduces to a very, very simple number. Which of you has done electrostatics already? Hitesh, you've done it?
No, sir, no.
Sanjana, have you done it? Sampath, have you done it?
No, sir.
Arian, have you done it?
Not yet, sir.
Vaibhav, Vaibhav, have you done it?
Yes, sir.
What is this number 1.4 pi epsilon naught? What number does it take in the SI system? 9 into?
10⁻⁹.
Very good. This, when this is taken in coulombs, and this in meters, and this is in newtons, and this fellow takes the value 9 into 10⁻⁹ SI units. Means if I want the units of this, it is Newton, it is meter square upon Coulomb square. This, I'm just writing SI. This expression takes this wonderful crisp number when I'm making calculations. When I'm in a vacuum. So if I take Q1, Q2 separated by a distance r in a vacuum, then I write the expression 1/4 pi epsilon naught, which takes this. That is why if you get a number 2 here somewhere, don't cancel this 2 and 4 and feel that you are being very educated. You leave 1/4 pi epsilon naught as it is, because it has this number, which is easy to multiply and divide in the exam or in your calculations. Okay, now let us look at this. 1 is 1, 4 is 4, pi is pi. Epsilon naught. This was called permittivity. Since we are in a vacuum, permittivity of free space. Permittivity, something to do with permission, something to do with something permitting. And I told you that this K had something to do with the medium. Then this is not medium, this is not medium, this is not, this is something to do with the medium. permittivity of free space. It is the permittivity of the medium, which is the free space, that's the vacuum. What could it be? Don't get very deep into it, but you can give a self-explanation this way, which I will just explain. For the time being, accept the fact that this is called epsilon naught. Epsilon naught is permittivity of free space, which we write when we are in a vacuum. If we are in any other medium other than a vacuum, then we write permittivity, epsilon. So if the examiner uses this epsilon naught, you know he's in a vacuum. If he gives you permittivity of some medium, like some gas, then you say 1/4 pi epsilon, and you will use that value. So for a vacuum, approximate value of the permittivity is 8 point, very approximate, 85 into 10 raised to minus 12. All SI system, some SI unit. How do you get the SI unit of permittivity? Just take permittivity here, take everything else and just write its units. It doesn't matter. It's not important. Just understand that in the international system of units, this whole thing takes the value 9 into 10 raised to 9, and the permittivity, the epsilon naught, has an approximate value this. You don't have to know it. After some time, you remember it. Let us try and understand what this permittivity is. Just slight feel of it. You will get to know it very well towards the end of electrostatics. When we talk about Faraday's contribution in understanding this term, which will be towards the end of electrostatics, just before we start moving charges from static conditions to moving, that means current electricity, just before that. You'll get to know this a little better. And then you will get to know it even better when we come towards the end of electromagnets. That's the interesting bit of this chapter, which has been put in such an order that there are many, many terms which you will not get to know them so well unless you read the whole of electromagnets. Okay, accepted. Let us try and understand this a little more. Supposing I were to take two charges, Q and Q naught, separated by a distance r. I'm still using only particles. Small specks which have charges, a small particle which has charge value so much, which we know is the excess imbalance charge. Okay. We know that the electric force between this will be, if it's a vacuum, 1/4 pi epsilon naught Q naught upon R squared. Let us develop a new idea where, try and understand this. There was no Q naught here. There was only Q. Q naught was far away. Far away. Then Q naught slowly was brought here. As soon as he was brought here, he experienced a tug, an electric force. So how did Q naught, or how did Q know that Q naught has come? It doesn't have ears, it doesn't have eyes, it doesn't have a nose. How did Q know that Q naught has come? Or how did Q naught know that there is a Q here? That it suddenly started experiencing it. It means that even in absence of Q naught, the very presence of Q, the intrinsic property Q, charge, had already disturbed this space, had influenced the space. Switch this property off, gone. Switch it on, there. And when this fellow came within this region of influence of Q, when it came within this region of influence of Q, it experienced a tug. Which means Q had already set up region of influence, means we will define it by the word electric field. Just like in the chapter of gravitation, we had the earth and we said that anybody any object which comes within the influence of this property M, which comes within the gravitational field, the ball with the mass m dash will experience a tug, a gravitational force. An equal and opposite gravitational force the earth is going to experience. Same force both experience. Both start moving towards each other, the earth and myself, or the ball and the earth. But the mass of the earth is so huge that F upon m, the acceleration will be in micro millimeters, whereas the mass of the ball is so small, the same force divided by a smaller mass, you will be able to perceive the acceleration, the gravitational acceleration. Whereas you don't experience the earth moving up, because it is there, but it is in micro millimeters. Let's come back. So the same concept of gravitational field, electric field. I switched on the property M, gravitational field. You come within the gravitational field, and if you have a property mass, you will experience a gravitational force. You come within the electric field of a charge or a collection of charges, then when you come within that, you will experience the Coulomb's electric force. You will experience the electrostatic force if charges are static. Very good. So let us understand this permittivity through the concept of this field. So the moment you set up the charge, the region gets influenced. Then you bring another charge, it also has its field. Both the fields merge. The medium allows certain permittivity of this influence. It is something like that. For the time being, we say that. It is the medium which is connected with epsilon or epsilon naught, which is to do with the permittivity, which is to do with how the charges are going to influence the space around. Just keep it in mind for the time being. Now, as we move towards the end of electrostatics, you will know better stuff. Okay. Another thing that was noticed is that epsilon naught, epsilon of a medium is always greater than epsilon naught. The permittivity of any medium other than a vacuum is always of a bigger value. How? If this is a vacuum between Q and Q naught, if this is a vacuum, then this is the electric force, sir. If I change this by now pumping air, so air is there in this medium, then suddenly I find the electric force drops. I've changed the medium, I've changed the permittivity, it's become this. When it becomes this force between the two charges Q1, Q0 falls, becomes less. So obviously it means this is greater. This is greater than this. So we will accept that the permittivity of any medium other than a vacuum is always greater than the permittivity of free space. That means when you take two charges Q1 and Q2 or Q and Q0, the electrostatic force between the two is the greatest. Then if Q and Q0 were taken in any medium at the same distance r, the electric force, the electrostatic force between the two would have been much less. Okay, accept. Experimental evidence has led me to accept the fact that this factor epsilon is greater for any medium other than a vacuum. For a vacuum, it is the smallest. And for a vacuum, the approximate, very, very approximate, you'll see that there is a reason behind it, very, very approximate values. Okay. Later on, Faraday will teach you how to find the permittivity of a medium. That's when you will probably get to know it a little better. But it is fair enough to say it is something to do with the electric field which is being set up in the medium. It is something to do with that permittivity allowed. See, like that. Okay. This is what we did last time. And then I told you that let us further develop this idea of the electric field or electrostatic field. So I said, let us take two charges, this and this, at a distance r. Let us accept the fact that the electric force or the Coulomb's force via the Coulomb's law is this in a vacuum. And let us develop this idea of the electric field. From this, I'm going to develop two ideas. One is the idea of an electric field or electrostatic field, and another idea I'll develop from this is the electric or the electrostatic potential. Alphabet B. So which means that if I have a charge, then the space around will have an electric field and the space around will have an electric potential. Because the charge is static, I call it electrostatic field, electrostatic potential. I developed these new concepts. The concepts where this guy is a vector concept. This is a vector concept, and this is a scalar concept. Why am I doing it? I have two charges, I know the force between the two charges, and the story is over. Why am I getting into this? Because by creating these two new concepts, I will get to know the behavior of my charge better and better. It will enrich my knowledge of basically that intrinsic property charge. That's why it is being done. As I told you last time, kindly understand that the way in which I am going about electromagnetism, let us say the first area which your books call electrostatics, is a wonderful way in which the flow has to be developed. You will soon find that not only we will cover whatever your institutions are doing or are going to do, but we will be able to remember and we will be able to have a better grasp of our intrinsic property charge, and we will be able to very seamlessly move from electrostatics to current electricity to magnetism, etc., without feeling that we have moved into a different zone, because there will be a continuity maintained. All right. And this is how it has to be done, honestly speaking. If you want to do well in electromagnetism, which is almost 50% of your syllabus, which means if you take your physics paper from the toughest exam in this country, you will find 50% of the questions are from electromagnetism. It's worth it. It's worth getting a grip of the same. And it is easier than mechanics. Much easier. All right. Let us develop these two ideas first. Let us first define these two ideas. Once we define them, we will keep going back to our charge. To define this, all definitions will be in a vacuum, sir. After some time, when I change from vacuum to some media, the only fellow who will change is the permittivity. All right, so don't worry about it. Let me get rid of Q naught. If I want to get rid of Q naught, I will just shift it here. See, from the right side is gone. I've created a new entity. Because this is a vector and I'm dividing it by a scalar, I got rid of it on the right side. I pulled it out from here, I put it there. I created a new physical quantity, the electric field, the electrostatic field. And what's on the right side? No Q naught. Q is alone. R is there, yes. But I've shown this as a vector, so magnitude, because I'm not showing a vector here. What is it? What is it? I've got Q, which I call source. At a distance R, I've got a point P, which I call the field point at a distance R, and here I have the electric field. The electric field in magnitude is proportional to the intensity of the source. I double the charge, 2Q, E becomes twice. Half it, E becomes half. And it's inversely proportional to 1 upon R squared. I double R distance, E falls 4 times squared. Reduces very fast with the increase in distance because squared, inversely proportional squared. Source. Switch on the source, switch it on. At a distance R, at the field point, I get E. The magnitude of E is 1 upon 4 pi epsilon naught Q by R square. But it's a vector. Yeah, it's a vector. In electromagnetism, there is a certain nomenclature, and Q naught is normally associated with what we call a test charge. Q naught tends to 0. It is very, very small. So I take a test charge, Q naught. Very, very small value. It does not have its own influence. It does not create an electrical field of any worth mentioning value, which is so small. It is just a test charge. In the nomenclature of electromagnetism, a test charge is positive, always. The moment the examiner mentions he's taking a test charge, it means he's taking a small positive charge, which is a tester. What does it test? When you take Q naught and you bring it here at the field point, if this is positive, test charge is always positive, it will get pushed away. That becomes the direction of the field there. If this is negative, the source, and you bring a test charge, if it gets pulled, that becomes the direction of the vector concept of the field. I can map a field I had a collection of charge. Could be a big sheet which was charged. And I took my tester because the region was influenced. There was a field set up by this collection of charge. Field set up. The excess charge on this sheet, this collection, excess charge. Set up a field. I took my tester, I got an arrow like this at this point. I took it here, I got an arrow. I took it here, I got an arrow like this. Then I made number of such arrows. And then I drew a line such that these arrows were tangent. And then when I took the tester and I put it here, it gave me this. This line, which was tangent to all these little vectors which my tester gave me, this line becomes the electric field line. Electric field line. Electric field line. For this collection of charge, I got the electric field configuration. Mapping of the field. Who helped me do it? Always a positive. This is a convention set by the people who laid down the chapter of electromagnetism, the rules. Good. Great. I'm filling up, filling up. Source, field point. A field is set up. The variation magnitude of the field with respect to R is a hyperbolic variation. When you come very close to the charge, it takes an infinite big value. When you go far off, it tapers off to zero. What about this idea? So I have a source at various points, R1, R2, R3. I have the field and I know how to handle it. I'll get the direction of the field by using a tester. What about potential? This is a scalar concept. What is this? It is obviously will be based on scalar concepts. Scalar concept in the chapter of work energy. Let us develop it. I need space. Let me develop this idea. At this stage, it becomes important for me to mention that in the whole of physics, there are these three conservative forces. One is the gravitational force, Newton's gravitational force. The other one is Hooke's spring force. And the third one is Coulomb's electric force or electrostatic force. These are the three conservative forces that you will come across in the entire physics. What we mean by conservative forces, we have a fair idea. That if this force were to take this object or were involved in the work involved in this object, that means if this object was shifted from position 1 to position 2 via this path, let us say, force displacing, some work is done. And this is the only force involved. There are other forces, but they were not contributing to the work. The only force which was contributing to the work was the gravitational force. And I calculated the work done. Force into displacement, etc. I got it. Then, when I return from 2 back to my original position via some other path, I did work W2. Same force involved. To my surprise, I found that W1 was equal to W2 in magnitude. In sign, they were opposite, which means if you accept the fact that the definition of work means change in energy. Kinetic energy changes, work is done. Potential energy changes, work is done. Spring, elastic energy changes, work is done. Frictional energy changes, work is done. So every time energy changes, work is done. Who changes the energy? Force. What does the force do? We find that the force creates a displacement and energy changes and we get work. That's how we see it. We find that if work was done from year to year, the energy changed, then the work was found to be, let us say, positive, then this work was found to be negative, though they were equal in magnitude. That means if I took this object from 1 to 2 and then came back to 1 via some path, any path, I found that the network is 0, which means there was a change in energy and then I recovered the energy. So overall, there was no change in energy. Hence, because there was no change in energy means work is 0. Which means the energy was conserved back. And hence the forces which carry out this kind of conservation are called conservative forces. This force does similar things. This force, Hooke's spring force, does similar things. And now Coulomb's force also is a conservative force. Now, if you go back into your study of the chapter of scalars, which was work energy, you find that the work done by the conservative forces was always minus del U, and the conservative forces were always involved with the alphabet U. Gravitational potential energy, elastic potential energy, electric potential energy, or electrostatic potential energy, or electric potential energy. Potential energy was given the alphabet U, and these guys were connected with that, and that was always with this. So I accept that now work is being done by the Coulomb's electric force, which is equal to the electric force dot ds or dot dr to be more precise, since I'm using R. I have now my electric force between two charges Q and Q naught at a distance R given by this in magnitude. Whenever we develop certain formulas, there is a convention set by the people who frame the entire subject. In electromagnetism, when we set up formulas and when we derive certain formulas, we always take the charges to be positive. So here both these charges are positive. Had we taken Q1, Q2, let's take Q1, Q2 to be more comfortable, all right? So for the time being, let me take then the Coulomb's force is 1/4 pi epsilon naught. I'm not going to use K, and I don't want you to use K because you'll make certain real strong blunders in the big exam, all right? Q1, Q2 upon R square. This is not E, all right? This is epsilon naught. Then if both these are positive, that means the force is going to be like this. Repulsive force, right? So the force on this will be, let us say we only represent it on this for the time being, it will be equal and opposite. I'm just showing this. Then when I say R and I say dr with a vector, I'm giving it a direction. I'm just taking that little displacement dr outwards by using this as a reference. Then the force is outwards and dr is outwards, and f dot dr becomes f dr because the angle between the two is 0. So dot product has a cos 0. Please understand this way of discussion. This is how conventions are set slowly. Formulations are standardized. Then this becomes dot product removed. I've explained you. Both charges are always positive, that's outwards, and dr is taking one as a reference, outward radial vector. So dr, small bit of the radial vector dr. Put the values now. Take out what is not variables out. As I go from some initial value of R to some final value of R, please remember one thing, which I've been telling all the people who've been coming for my classes, that please work every week for at least 2-3 hours on calculus. Work in calculus 2-3 hours. Don't wait for your institution to do calculus. You work on it. Get to understand your functions, get to understand your limits, get to understand your continuity, and get to understand the simple methods of differentiability, and learn certain standard differential methods and certain standardized operations of derivatives, and also go ahead and learn something about antiderivatives, that is integrals, and certain standardized features of integrals. The derivative part of calculus, and there's an integral part of calculus, which is the antiderivative. They both together form what is known as calculus, which is part of your mathematics. Unfortunately, it should have been part of physics. In many, many countries, it's part of physics. So here it's been pushed into mathematics, so it's lost some of its essence. But calculus was developed by Newton. He was the inventor of calculus. And throughout physics, starting from the first chapter of kinematics, calculus is required all the time. Change in position with time, derivative of position with time, velocity, see, change of velocity with time, acceleration. It was a very, very dynamic science created by Newton. Graphically, it can be beautifully understood through physics. I've been telling my students that I'll give a talk, but I'm always falling short. Now I've come into the chapter of electromagnetism where I cannot do without calculus. I cannot do without derivatives. I cannot do without integrals. And again, I'm telling you, and again, if people want to know which are the good books to refer where and things like that, they can always talk to me. But it is mandatory. It is 35% of your syllabus. 30% is coordinate geometry, 35% is calculus, 65% gets over even on weekends if you're working in these areas within the next 4 or 5 months. 65% of your maths you'll finish. Rest is all algebras. I've been telling people, and some of you have taken my advice, and some of you have covered a major part of calculus, and I'm happy about it. And my advice continues. Just like here, I'm doing a little bit of integrals. I will be soon using a lot of calculus. And you might feel a little uncomfortable about it. But then probably that will give you a little momentum, and maybe you will get into spending time on weekends in calculus from the good books. All right, so we get this. Going from some initial value to final value of R, the variable. This is nothing but x raised to n. I can put R square as R raised to minus 2 dr. I can do that, which is this operation is this, and you can put the limits, initial, final, put the final value minus the initial value. And R raised to minus 2 plus 1, I'll get minus 1 upon minus 1, so I'll get minus. So I get 1 upon 4 pi epsilon naught q1 q2 upon 1 upon R initial final, and I've removed the minus out. So now I need space. Now, so I found out the work done by the conservative force, which is that. That means that is equal to, this is, yeah, minus 1 upon 4 pi epsilon naught q1 q2 into 1 upon R initial final. The minus and the minus goes, I'll only take this much now. And I will now get U final minus U initial delta U is equal to 1 upon 4 pi epsilon naught Q1, Q2 to 1 upon R initial final. I'm interested in finding this term, which I call electric potential energy. It's not electric potential, right? It's electric potential energy. Sometimes we say electrostatic potential energy. It doesn't matter. Because the charges are static, so electrostatic potential. I'm interested in the final value. Final position of Q1, Q2 at R. Initial position. I want to get rid of initial. Let initially Q2 be at infinity. That means R is tending to infinity. Far away, the energy is zero. There is no interaction between the two. There is no electric energy between the two. It's zero. Far away, R tends to infinity. Final R. Hence, when this put R minus 1 upon infinitive, that's zero. That means this is zero. And hence you get U equal to 1 upon 4 pi epsilon naught at any position R, Q1, Q2 upon R. Put R minus, put infinitive, zero. So you are left with this. I will put your electric energy, electric potential energy. Electric potential energy. Electrostatic potential energy because charges. I want this concept. You remember this. That if you have two charges, Q1 and Q2, separated in distance R, there is an energy. There is an electric energy between the two. Because obviously there'll be an attraction or a repulsion. So there is an electric energy. Electrostatic energy of this system of two charges Q1. It is always system. Potential energy. This duster has potential energy? Not correct. The duster with respect to the earth, this system has potential energy. Q1 cannot have energy. Q1 and Q2 together form a system which has energy, electric potential energy. If the charges are static, electrostatic potential energy given by this. Let's keep it in the mind. Good. So I developed the idea of this, and now I have developed an idea of U here somewhere. Two charges Q, Q naught. Instead of Q1, Q2, Q, Q naught R. Since it's energy, this is joules. I don't want Q naught. Joules per coulomb. Electric potential, electrostatic potential. Look at the right side. Charge source, distance R, field point, electric, and now I have charge source at distance R, at the field point. I have now potential. Potential is proportional to the intensity of the source. Is inversely proportional to 1 upon R. Joules per coulomb was given a short name to pay respects to the scientist volt, and potential is in volts. The electric potential is 10 volts, 20 volts. What is it? Joules per coulomb. Something to do with energy. There is a charge. It sets up a voltage. Wow. There is a charge. It sets up an electric field. What about the variation of voltage with electrostatic potential? Electrostatic potential, what about its variation? Slightly different. That is also hyperbolic, this is hyperbolic. But this takes longer time because it's just 1 upon R. This is 1 upon R square. This comes to 0 faster than this. Both are hyperbolic variations. So, there is a fantastic observation in the graph. E for a charge or a collection of charge at some point E became 0, but V was not 0. Possible. You can be asked this question. Are you people getting my sound correct, Hitesh?
Yes, sir.
Okay. So you remember that. You'll be asked this question in the interview. That is it? Can you have regions where E is 0 and V is not 0? Yes. You will see that. When I put down different configurations, line charge, charge on a circle on a loop, and when I take charge on a disk, and when I take charge on a wall, and then when I take charge on a spherical object, and I find out the electric field and potentials at various points, you will find that there will be points where E is 0, but V is not 0. This is a fantastic thing. The concept has been developed like that. Okay. Let us now look at it quickly as a summary. Just this. So what did we do? We said we wanted a richer grasp of this intrinsic property charge. And we decided to develop two concepts, a vector concept and a scalar concept. This is in newtons per coulomb. This is in volts, which is joules per coulomb. which is nothing. Source at distance r, at the field point, we are talking of this and we are talking of this. This is a scalar. This has no direction. This is just a scalar. Electric, we will find its magnitude, E proportional to Q, E inversely proportional to R square, 1 upon 4 pi epsilon naught Q upon R square. And then to give it direction, we'll put a test charge and see. Potential, it's just a scalar, just a number. From the formulations and definitions, did you notice this upon Q naught was E in magnitude? That means E into Q naught will be the force. Vector. So if somebody gives you at a point the field, and if you're carrying a charge Q dash into the field will give you the force there, the Coulomb's force. Similarly, from the definition of potential, U of the system, not charge, will be Q dash into the voltage. So if somebody says 10 volts into the charge there, Q naught will be the electric potential energy of the system. Which is the system? I put a charge Q dash here. So Q dash into V created a U of the system. What is the system? This plus this. These two form a system. This and this here form a system. Look at the formulation. Q dash, what is this? 1 upon 4 pi epsilon naught Q upon R. Oh, it is the system of two charges Q dash upon R. This U is of a system. The potential energy of the system. Of two charges. Potential of one fellow. Volts. Volts into coulombs. Joules. Grasp of the ideas. Charge into E. Electric force. Electrostatic force. Coulomb's force. Electrostatic potential energy. No problems. And keep using that word static. After some time, you'll get seasoned enough, you'll just electric. Very good. The idea has been developed for a point charge. A particle which has an excess charge, a point charge. The idea has been developed. We have to extend the idea from a point charge into a line charge. I could take a cotton string and I could put charges on it, or I could charge the cotton string. I want to know in front, when I stand in front of the cotton string, what is the electric field there? What is the potential there? I can take a string and make it into a loop. So I have developed it for one charge at a distance r. Charge, 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 charge. Line charge. Take this string and make it into a loop. And let us say it is positively charged. It could be negative. Loop. Then if I take the loop and I stand on the axis of the loop at point P, field point, because of this collection of charge, what is the electric field here? What is the potential here? Starting with a point charge. Point, calculus. At any point, at any distance r, what is the electric field here? What is the potential here? String, loop. Disk. Disk. Axis of the disk. At P, what is the electric field? What is the potential? Sphere. At R, what is the electric field? What is the potential? Hollow spherical shell. Certain standardized configurations of charge. Configurations of charge. Certain standard configurations of charge. Line charge, loop, uniformly charged. Disk, uniformly charged. Sphere, uniformly charged. It is non-uniformly charged. It becomes very difficult. So in your course, mostly it's uniformly charged. These are the standard configurations on which most of your numericals will be based. You have to know certain standardized expressions for the electric field and potentials for all these values, so that you can immediately write them down and then carry on with the problem, which you will get to know them quite easily because I will teach you how to remember them and how to use them. But the starting foundation is point charge and the formula. I will take a small charge dq, point charge, at a distance r, let us say. What is dE? What is dV? Then dV is equal to 1 upon 4 pi epsilon naught dq upon r. dE in magnitude is equal to 1 upon 4 pi epsilon naught dq upon r squared. This is the basis, the foundation. dq, 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 dq. dq, 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 dq. 1 dq, E, dE, dV, dq, dq, dq. Summation, integral dq, dq. Integral E, dE, dE, integral dV, 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 V, E. Calculus. Understanding how we are getting the standardized formulations for the electric field and the potential, the procedure is very important because he can create a non-standard situation. And if you know the procedure, you will be able to process that and get the expression for the problem given in the exam. The two-stage applications involve these standardized formats or configurations. Okay, we accept. Let us start. I'll stop here. But the whole idea is try and not miss classes, because now I'm going to go to the other configurations, the line charge, the loop, then the disk, then the spheres. That gives me a fantastic zone now and enough collection of ideas, and I can start throwing numericals at you and slowly developing a wonderful electrical element, the first one, that is the capacitor. I need the concepts of electric field and potential and these different configurations for me to design the first electrical element, which is the capacitor. And this is exactly what Faraday did. He showed the world how to design capacitors. Those combinations of conductors which can hold charge and hence which can hold electric potential energy. He defined this very word capacitance. He defined it, he formulated it, he quantified it, which you will understand only if you understand the whole concept of electric field and potential for these different configurations. It is important as to why we are doing it. One is to understand charge, why we are doing it, so that we can start designing the first electrical element, the capacitor. Then similarly, we will design the second electrical element, the resistor. And then as we move into magnetics and magnetism, we will define the third vital electrical element, the inductor. Then the capacitor, the resistor, and the inductor together are sufficient to form smart circuits, which is exactly what you find in your houses. Okay, sir, I will stop here since it's late. And